Hello, Chem 1B. This is Chapter 20, Lecture Video 5, and we're going to talk a little bit more about decay kinetics. And so we know now that radioactive decays are always a first-order process. What's a consequence of that is that the number of nuclei that we had in our integrated rate law in the last lecture video is actually linearly proportional to the rate of decay. And it's a lot actually easier to measure the rate of decay of an isotope as opposed to the number of nuclei present in the sample. So what we can do is we can substitute rate into the integrated rate law instead of this being nt, number of nuclei at time t, and n naught, number of nuclei initially. We can substitute in rate here, and this makes it a lot easier for us to determine things and do calculations because it's easier to measure the rate than the number of nuclei. You can imagine that, I assume, because in even a small sample we know there are crazy large numbers of atoms, therefore nuclei present, and it's very hard to count all those. It's a lot easier to measure the rate. Because of this very predictable rate of decay, we can use the integrated rate law and first order kinetics to calculate the age of rocks and artifacts. This is typically known as radiometric dating, and if you heard a couple years back, they actually dated the the Shroud of Turin and determined its age by using what's known as carbon-14 dating. There's also uranium-238 dating, which is pretty cool. And we're going to talk a little bit about radiometric dating in this lecture video. All right. One is carbon-14 dating. And carbon-14 dating is probably the most common of the types of radiometric dating that you're going to find for artifacts that were human-made. What the whole basis of this is that carbon-14, an isotope of carbon, not very stable isotope, is made in the upper atmosphere of the Earth. It decays via beta emission to nitrogen-14, which is stable, via this nuclear reaction, right? So we have carbon-14 decaying into nitrogen-14 and the release of one electron. Now, the reason why this can be used for dating a substance, it has a half-life of 5,730 years, so this takes a while, but it happens. The reason why we can use this is because all living beings contain the same ratio of carbon-14 to carbon-12, because we're constantly taking in carbon, either through food or through the air that we're breathing or through a number of different biological processes. And because of this, our carbon-14 ratio while we're alive stays the same because we're constantly intaking carbon. Every time we eat something, we replenish the carbon-14 and carbon-12 in our bodies. But as soon as we die, the carbon-14 in our bodies starts to decay into nitrogen-14. And so this ratio between carbon-14 and carbon-12 starts to change as soon as we're dead. Plants, animals, humans, what have you. This is all due to the fact that plants absorb C14 when they photosynthesize, and then we eat the plants, or animals eat the plants, and then we eat the animals. At some point, we're eating carbon-14, and it's replenishing that amount in our body. But once we die, we stop taking in carbon-14, and the carbon-14 we have starts to decay to nitrogen-14, which causes the ratio between carbon-14 and carbon-12 to decrease. We can use that ratio that we have at this point in time versus what it should have been back, when we were alive, to measure how long it's been since the thing died. This allows for the calculation of the age of that object. Now, for artifacts, most things that we make are formed from living people, right? So maybe we have like a papyrus scroll that we found in a tomb, and we want to figure out, hey, when was that papyrus scroll created? Now, we can't give you an exact time frame, but we can give you a range. We would be able to tell you when the papyrus that the scroll was made out of died. So when did they kill the plant and then make the papyrus scroll? We can tell that part. And that gives us a pretty good accurate reading for how old that scroll was. Or maybe we have a wooden casket. Well, we can find out when the wood was harvested from the tree, which gives us a pretty good idea of how old that object is. Okay, so let's do a problem on radiometric dating. Let's determine the age of an artifact. And because, I love me some Indiana Jones, I'm going to nerd out on this problem a little bit and say it's going to be an Indiana Jones problem. So, if you haven't seen Ark of the Covenant, the very first Indiana Jones movie, you should go watch it. There's a little bit of a spoiler alert. He beats the Nazis. So after he stops the Nazis, the Ark of the Covenant, and saves the Ark of the Covenant, Indiana Jones wants to determine, hey, how old is this artifact? And so I looked it up. I Wikipedia'd it. The Ark of the Covenant was theorized to have been made from shittim wood, which is an Arabic type of wood, I believe, in that area of the world, because that would have been where it was made. And so kind of nerded out a little bit on this problem. Nonetheless, the wood had a decay rate of 9.89 disintegrations per minute per gram of carbon. And if we know that living organisms have a decay rate of 15.3 disintegrations per minute per gram, how old is the Ark of the Covenant? So there's a couple things that we need to have here. We need to know that the half-life for the decay of carbon 14 to nitrogen 14 is 5,730 years. This was given on the previous slide, and I'll give this to you on the test. You don't need to memorize it. We also need the first order integrated rate law, right? So the natural log of rate at time t is equal to the natural log of rate at time initial minus kt. And so we're going to try to solve for t here. We have both the rate initial and the rate at time t, right? So rate at time t is the 9.89, and rate at time 0 is the 15.3 value. We need k in order to solve for t. So how do I get k? Well, I also know that the half-life of a first order rate law, or first order reaction, is natural log of 2 over k, which means I can plug that in, right? That 5,730 is equal to the natural log of 2 over k. And k, if you solve this out, is equal to 0.000121 years to the negative 1. So now I know k, and I know my rates. So I can plug all this stuff in, right? So I know that the natural log of 9.89 is equal to the natural log of 15.3 minus 0.000121 inverse years times t. And we want to rearrange and solve for t. And if you do this, you get t is equal to 3,606 years. However, sig fig wise, we should change this to 3,610 years because we only have 3 sig figs. Not a huge thing, but it is a background thing. And so that gives us the age of the Ark of the Covenant. Now, there's another type of radiometric dating that we can use for non-living things like rocks, ceramic ware, and stuff like that. It's called uranium 238 dating. Uranium, like we talked about in the beginning of this lecture, this chapter, decays eventually into lead. And we can measure how long that takes. And so if we have a sample with a lot of lead in it and uranium, it's likely that all the lead in the sample came from the fact that the uranium was decaying. and we can calculate it that way. If you're interested in it, it's definitely in the textbook. I just not going to cover it here or ask homework questions about it. So